Okay, so in the magnetic field topic, now we have to discuss a very important section, which is 20.3, which is force on moving charge. So in the force on moving charge, we'll look for the direction of force on the charge moving, how the force acts on moving charge, in which circumstances or scenarios the force is not acting on the charge. And then we have to look for this expression, which is F is B times charge times velocity into sine theta. This is the expression for force on the charged particle. And then we have to look a very important thing, Hall voltage. This is the device which is used to measure Hall probe is the device which is used to measure the magnetic field strength directly, like ammeter is used to measure current. In the similar way, Hall probe is used to measure the magnetic flux density at any point. And then we'll understand the use of Hall probe to measure the magnetic flux density. Then we have to describe the motion of charged particle moving in a uniform magnetic field perpendicular to direction of motion of particle, like the simple way, like how the charged particle is moving in the magnetic field. And then we have to look upon the electric and magnetic field in velocity selector. Velocity selector is a particular device. It is instrument widely used in physics and chemistry, and this is used to measure the this is used to identify the isotopic forms of newly discovered elements. Okay, so here is the first thing about the topic, force on charged particle inside the magnetic field. So first of all, we can see here that there is a uniform magnetic field which is represented in the form of series of equi-spaced, equi-placed crosses. These crosses means that the magnetic field is uniform as the crosses are equally spaced and the magnetic field is pointing into the plane of paper. So the cross means magnetic field is into plane of paper. Okay. And as the crosses are equally spaced, so it means that the magnetic field is uniform. Now, there are some scenarios. So let me first tell you about two scenarios. The first scenario is the static charge. If the charge is static inside the magnetic field, then it is not going to experience any force. The magnetic force acting on it is zero. Like anywhere, like let's say a positive charge is placed anywhere, a negative charge is placed anywhere, alpha particle is anywhere, and all of them are at rest. So it means that although they are inside the magnetic field, but magnetic field is not interfering them. Why? Because the charge is at rest. So the static charges will not experience any magnetic force. The second scenario is moving charge parallel to magnetic field. Moving charge parallel to field. Okay, so when a charge is moving, but it is moving parallel to the field, what does that? Like, these crosses means that the magnetic field is moving into the screen away from you. Like you are, at the moment, you are like a north pole and some south pole is behind the screen. So the magnetic field is coming from north, entering in the screen and going behind that. So crosses means that magnetic field is going away from you into the page. So let's say a charge is traveling parallel to that. So it means the charge is moving into the screen parallel to the magnetic field lines, or it can be that the charge is coming out of the screen. It is moving, but it is moving exactly parallel. Like parallel in a way that if this is the magnetic field line, the charge is also moving like this. If this is the magnetic field line, the charge is also moving like this. If this is the magnetic field line, charge is also moving like this. So this shows that charge is moving parallel to this field. So when the charge is moving parallel to magnetic field, again, no magnetic force acts on the charge. So it would not experience any force. So these are the two scenarios in which there is no magnetic force acting on the charged particle. Okay, the next scenario now in which the charge is going to experience the maximum force. And that scenario is that if a charge is moving and it is moving perpendicular to the field, like the way this charged particle is coming, right? And it is coming, let's say, we can say that it is coming perpendicular and it is entering in the magnetic field at right angle. It enters in the magnetic field. As soon as it enters in the magnetic field and it reaches at a point, okay, let's just remove all of that. Okay. So now look, as soon as it reaches this point P, it is going to experience a force. The charge is having mass m and it is moving with a speed u. So when it enters at point P, it is going to experience a force. And that force is magnetic force. You can find the direction of that force using Fleming's left hand rule. So if, let's say, the charge is positive, which is represented in the brown line. So if a positive charge is moving over there, in which direction the force will act at P? So force at P. So again, we use Fleming's left hand rule. So use again the rule. Point your first finger into the screen, left hand, first finger into the screen, second finger towards direction of the charge, towards the direction of positive charge, that is towards your right side or towards right up side of the screen, and hopefully your thumb should be pointing towards the top of the screen, right? Upwards, towards the top of the screen, like this.
Yes, sir. Yes.
So it means that magnetic force is acting perpendicular. Magnetic force is acting upwards. So this magnetic force is perpendicular to the direction of motion. So this magnetic force is actually a perpendicular force. And we know that whenever a perpendicular force acts on object, that object started moving along a curved track, because perpendicular force makes the object move along curved track. So due to this force, the charge would start moving along a curved track and it will start moving upward because the force is upward like this. On the other hand, if this charge would have been a negative charge, suppose this is a negative charge now. So when this negative charge is coming at point P, it will experience a magnetic force again. In which direction the force will be acting? You have to use the Fleming's right hand rule now, or you can use the Fleming's left hand rule as well. That's fine. So use Fleming's left hand rule, but this time point your first finger into the screen, towards the screen, and you have to point your second finger away from the movement of electron. So your second finger should be pointing this way. Why? Because we know that if positive charge moves this way, negative charge moves the other way. Or if the negative charge is moving towards your right, the positive will be moving towards your left. And as we know that Fleming's left hand rule and all the other rules are actually used for conventional currents. So that's why you have to point your second finger away from it. So point your first finger inward and then gently twist your hand in towards your palm. And then when you twisted your hand, so you can clearly see that your thumb would be pointing in downward direction, isn't it?
Yes, sir.
So it means that the force on electron will be acting in downward direction, and due to that, the negative charge is going to deflect in downward direction. And it will move along a curved track inside the field. As soon as it leaves the field, it started moving along straight line. And same is for the other. When it leaves the spin, it would started moving along straight track. Why straight? Because outside the field there is no force, so there is no point in moving along the direction. So now, if we look at this, a moving charge particle in a magnetic field experiences a force whose magnitude depends upon the following factors. The first factor is the magnetic field strength. The second factor is the size of the charge. The third factor is the velocity of the particle or the speed of the particle inside the field. And of course, the important is the angle theta, which is like in terms of sine theta, and this is the angle between the velocity of the charge and magnetic field strength. So when you combine the factors, you got the formula, which is F equals BQV sine theta, and you can replace that constant with K and equal. So K is 1 here. So then we say that F is BQV sine theta, and this equation is also provided in the data booklet. And graphical dependence is the same. Force versus B, straight line. Force versus charge, straight line. Force versus velocity, straight line. And force versus sine theta, straight line. And then force versus theta, it's not a straight line, but it's a curved line, as we have discussed for the current carrying wire as well. Okay, there is another way to find have this expression. You know that the force for the current carrying wire is like this when it is placed in the magnetic field, and you already know that what I is equal to. So I is equal to Q by T, because it is the charge, rate of charge flow. So now what we can do is F is BQ and then L by T sine theta. You can just pair L and T. And you know L over T, L is the length and T is the time. So it means that we can say that this magnetic force is equal to BQV, because L over T is speed. So BQV sine theta. So that's how you can derive this expression as well. Like this is a second way to get this expression. The first is the simple factor way to make the formula, and the second is this way. Okay, now for the direction of the magnetic force, we use Fleming's left-hand rule, FBI. You have to point your, the thumb will tell you the direction of force on charged particle. You have to point your first finger towards the direction of magnetic field, and you have to point your second finger towards the current, but that should be the positive charge. In case of the negative charge, you have to place your second finger against that. Like the first finger is like this, second finger is the current, which is positive, and the thumb will give you the direction of the force. So you can apply the rule again here. For the positive charge, the force is upward, that's why it moves upward. For the negative charge, the force is downward, that's why it curled in downward direction. Okay, the next thing is radius of the path traced by charged particle in a perpendicular field. Sometimes it happens that when a charged particle enters in the field, that charged particle is trapped inside the field. That is trapped inside the field, and I can make a diagram for that. So let's say if the series of crosses represents the uniform magnetic field, which is pointing into the plane of the paper, like this. And then let's say a charged particle is coming, and let's say the negative charge particle is coming. It enters here, and then it experiences a force in downward direction, and it started moving downward direction like this. So as electrons are less in mass, so they experience the greater force, that's why they bend more. In case of the positive charge proton, they have higher mass, that's why they bend less. So electrons are going to bend more. And now as this curved track is there, so of course this curved track would be having some center as well, and then if this curved track would be having some radius as well. So that's what we are talking about here. So since a moving charge particle traces a curved track in the perpendicular magnetic field, so centripetal force acts on it. We know that whenever object moves along circular track, of course centripetal force acts. The origin of centripetal force is the magnetic force. So actually this centrifugal force is provided by the magnetic force. So we say that the magnetic force is BQV sine theta, and the centripetal force, in circular motion, we studied that it is mv squared by r. So this v and v are cancelled away. So you are left with BQ equals mv over r. And from here you can make r as a subject. So comes to be mv over BQ. But you know that this mv is equal to momentum, product of mass and velocity. So we say that the radius is equivalent to momentum of the particle over b into q. So this is the expression for finding the radius of the path traced by the particle when moving inside the magnetic field. Okay, so then a simple question is there. Calculate the ratio of the radii of the path traced by the alpha particles and the negative beta particle if both enter with the same velocity in a perpendicular uniform magnetic field, and the elementary charge is given, which is charge on a force beta particle. Unified atomic mass unit, which is mass of one nucleon, is given, and rest mass of electron, which is equivalent to mass of beta, is also given. So we know that the expression is r radius is mv over bq. So this is for alpha, mass of alpha into speed of alpha over bqv, and then rb is mv over bq. So b and b are cancelled away because they are same. V and v are cancelled away because they have same speed. So the ratio becomes equal to m alpha over q alpha, and then qb over mb, because you took this two upwards and then you reciprocate them. Now you have all the values. So mass of alpha 4 into mass of nucleon divided by the charge on alpha. So this thing is important, that if we talk about alpha, so the mass of alpha, as it is equivalent to helium nucleus, He42, so its mass is equivalent to 4 nucleons. So you multiply 4 with 1.66 into 10 to the power minus 27 kg to get the mass. And to get the charge on alpha, what we do is alpha is having a charge of 2. So the charge on it is plus 2 E. That's why the charge is 2 into 1.6 into 10 to the power minus 19 coulomb. So that's why it is done like that. And of course, for the B, for the beta particle, it is 1.6 times 10 to the power negative 19, and its mass is equal to rest mass of the electron. So this is cancelled away, and then the ratio is like this, 3.64 into 10 power 3. That is the ratio. Okay, now path of the charged particle in mutually perpendicular electric field and magnetic field. So that is quite simple again. You can look here. This is the positive plate, and this is the negative plate. So this is the electric field, and you can see that the electric field is pointing in downward direction. The EF, electric field, is in downward direction, and the series of crosses are there, which represents the uniform magnetic field, which is pointing into the plane of paper. So both the magnetic field and the electric field are perpendicular to each other. Okay, so in this case, if a positive charge particle enters the field and it will not deflect, it will straight away move straight. So we can say that when it is moving straight, the electric force acting on it is in downward direction. So downward electric force. And then applying the Fleming's left hand rule, you can see your first finger should be into the screen, the second finger towards your right side, and the thumb should be upward. So it means that the magnetic force is acting in upward direction. So upward magnetic force, if the charge is not deviating, it is moving straight through the field. It means that the magnetic force, upward magnetic force, is equal to downward electric force. So magnetic force is BQV sine 90, and electric force is EQ, because electric field strength is electric force per unit charge. So electric force is QE then. So that's why it is written EQ. So this Q and Q cancel away. So BV is equal to E, and then this V is equal to E over B. What is V? V is the speed. It means that the speed of the charged particle can be determined by dividing electric field strength with magnetic field strength. Now on the next thing, the same field, but the charge is moving upward. If the charge is moving upward, of course, magnetic force is bigger than electric force. That's why it is moving upward. While if the charge is moving downward, So we say that the electric force is greater than the magnetic force because downward is the electric force. That's a simple thing. Now, again, the same thing. If the negative charge is moving in the field and it is not deflecting, so being negative charge, the electric force is in upward direction, and obviously the magnetic force should be in downward direction. So both the forces are equal. So again, it's the same thing. P is equal to E over B, just like the positive charge. And if the negative charge is coming down, of course, it means that the magnetic field strength is greater than electric force. And if the electric charge is going up, negative charge is going up, it means the electric force acting on charge is greater than its magnetic force. Okay, last thing. What is specific charge? Specific charge. So charge to mass ratio of a particle is known as its specific charge, Q by M. So this Q by M is the specific charge. Like let me tell you the example, proton. If you want to find the specific charge of proton, you have to write the charge on proton, which is this. You have to divide it with the mass of the proton, which is this. This is coulomb, this is kilogram. So you get the charge to mass ratio for proton. If you want to get charge to mass ratio for electron, what you have to do is you have to write the charge on electron, which is the same as charge on proton, but the mass of the electron is very less. So that is like this. So that's how you get charge to mass ratio. In order to derive the expression, magnetic force equals centripetal force, VQV is mv square by r, and then from here we can make Q over M as the subject. So Q over M is equal to V over BR. Like V is the velocity of the charge, V is the magnetic field strength, and R is the radius of the curved track. So by doing this, we can find charge to mass ratio, right? So till now it's enough. Now in the next session, we are going to study the last few topics of this chapter, and then we will move on to next important and last like Hall prop. One Hall prop topic is remaining. That is the important topic for this chapter, and then we will move on to electromagnetic induction. That will be the last chapter for this section, which is magnetic field. So